Hi, I'd like to start by thanking the organizers for having me and putting together this really interesting and timely symposium. My name is Miles Stoudenmire, and I'm a research scientist at the Flatiron Institute in New York. I work on tensor networks for quantum systems, but also for machine learning applications for a number of years now. My talk's titled Perspective on Tensor Networks for Machine Learning, and the idea of today's talk will be to review tensor networks for machine learning as a field, focusing on areas where I think some of the most interesting developments have been going on, but really with the goal of trying to look ahead and try to guess at where the biggest opportunities are in the future. So I'll give an overview very briefly, then talk about architectures that are beyond finite matrix product state tensor networks that people are exploring now and some of the applications. And then I'll talk about some progress in algorithms through the lens of a particular toy dataset called the even parity dataset, and two works on that, and what that says about the potential to do theory with tensor networks. So first of all, where can tensors appear in machine learning applications? So where do they generally turn up? One way they turn up is actually representing the data itself. And this is something that tensors or the tensor perspective on machine learning is used quite a lot. So you can have image data where you have tensors with three indices, where say one is the x coordinate of pixels, another index is the y coordinate, and then a third index is the RGB color value. Or you could have things like heterogeneous data, like medical data, where you have different patient characteristics along each dimension of the tensor. And then the idea is that all the data is assembled in or thought of as one tensor, and then it's analyzed to get some insight into structure of the data or to infill missing data. Another example where tensors are used or a tensor perspective is taken is in some interesting work in recent years, viewing the weight layer of a neural network not as a very big matrix, but actually as a tensor. So the idea here is if the weight layer is, say, 2 to the n by 2 to the n matrix, instead you can view it as a tensor with 2n indices, each of dimension 2. And then you can try to compress this tensor to get some kind of efficiency advantage or maybe generalization advantage when working with neural networks. And finally, there are certain cases, interesting and powerful cases of kernel learning models or Gaussian process models, where the weights naturally have the form of a high order tensor, even though it's not commonly talked about this way. And this is a place where actually, in this setting, is where tensor networks have seen quite a lot of use, and most, if not all, the examples that we've heard about today or hear about more fit into this framework. So then when you encounter these tensors, whether they're weights inside a neural network or outside or of data, why is a tensor network a compelling tool to use, and what is a tensor network? So a tensor network is just a factorization of a huge tensor into a bunch of smaller tensors that are then contracted together over sets of shared indices, and then some indices are uncontracted, and these are the ones that are the original indices of this kind of ideal large tensor. So instead of working with this full tensor that might have n indices, think of this as being 40 indices or something like that, or 100 indices. Instead of working with this full tensor, which would have an exponential cost, working with this tensor network reduces the cost in many cases to just polynomial, both in memory and time. But it can also give theoretical insight into the structure of data or the structure of a problem. It can give tools for techniques like estimating missing entries, filling in missing entries, or it gives you different interesting scalable optimization algorithms for machine learning tasks. So there's lots of different reasons why tensor networks are a nice tool to introduce. And when tensor networks are talked about, I'll be brief on this part. It's very common to use Penrose tensor diagram notation, where a tensor is shown as a shape and its indices are lines. So examples are you have a vector with one index, or a matrix with two indices, or an order 3 tensor with 3 indices. And this is a fully rigorous notation that's equivalent to classical index or tensor notation, but it's just much more convenient and for many reasons, and more insightful. And the main rule of tensor diagram notation is that whenever these index lines are joined, that implies a sum. It's similar to drawing this guide for the I line in traditional notation. That becomes this index line over here, and it implies that this index j, in this case, is summed over. And then when you use this notation, it's common to just not name the indices that are summed over, or even the other indices, because it's clear often from the topology of the network what's really happening with the sums, and the letters are no longer needed. So that can really lighten the notation quite a bit. This is an example where you have two matrices with two indices each, summed over both of their indices, and that's the trace of a product of two matrices. This is an example of a matrix vector multiplication in index or diagram notation. Now, in terms of families of tensor networks, the seminal example of a tensor network and the best understood is called a matrix product state, or alternatively a tensor train tensor network. And the idea is you take a tensor with n indices and you factorize it, or think of it as being expressed as a chain of tensors, a chain of n tensors that are linked together by one common index between them. So most of the tensors in this chain end up having 3 indices, as you can see. And the key thing to know about matrix product state or tensor train factorizations of tensors is that their main control parameter is the size of these artificial internal indices that are introduced in the factorization. So this size, called the bond dimension, is often notated chi, and if chi can be taken to a modest value, say 10 or 100, and still get good results in the sense of whatever task you're optimizing this tensor for, or representing some original ideal target tensor, which would be like the one on the left, if you can do that adequately for a reasonable value of chi, then you obtain a massive compression over using this full tensor. So the full tensor, if each index has dimension d, would have d to the n entries. So that could be something like 1 trillion entries if you have the case of d is 2 and n is 40. But if you work with the MPS over here, then the idea is you would have a very mild polynomial overhead in the bond dimension. So you just have to store and manipulate sets of small matrices that are maybe 10 by 10 or 100 by 100, and just store something like 2n of those matrices. It's a very, very light overhead. But you can still have incredible modeling power with this setup. And they're very flexible too. You can do very interesting tasks like summing the MPS while always keeping them in compressed form, summing 2 different MPS. Or you can multiply these MPS by matrix-like MPS that are called MPOs in an efficient way, always again keeping things in a compressed form. Or if a matrix product state represents a probability distribution, you can sample from that distribution in a perfect sampling algorithm where there's no autocorrelation effects in the sampling at all. So they're very versatile and have a huge amount of interesting algorithms that are basically ideal for them and very efficient. And what's more is that we have in quantum physics, where these have now been used for quite a while, a very rich and deep theory about which tensor networks, including MPS but other ones, are best suited for particular data. But here by data, what I mean would be something like observations of a quantum system, like samples from a certain quantum system. So we know things like that in basically all 1D quantum systems where correlations are short range in 1D, that these can all be described by matrix product states, the distribution of these quantum systems. And then there's a slight correction when the system has critical or power law properties that needs a hierarchical kind of tensor network called a Mira. And then in 2D, there's an analog of matrix product state called a PEPT tensor network that's known to cover a very large class of quantum states there. So this just really goes to show the depth of theoretical understanding that's been obtained by the physics community. So if we think of that as being a story about one kind of data, then perhaps this kind of theoretical understanding could be obtained for data outside of quantum physics too. And I think we're already starting to see that happen. So then most broadly, even though tensor networks have kind of a quantum mechanics pedigree or history to them in part, really I think the best way to think about them is nothing but a very general tool for linear algebra in exponentially high dimensional spaces. And when you're thinking about them in this way, outside of quantum physics, notions from quantum physics like entanglement entropy can instead be viewed as just a softened measure of rank, like analogous to matrix rank. So it's something that has a kind of a quantum pedigree, but really we could take a broader view of it, and I'll come back to this point. Okay, so that was just a very lightning introduction to tensor networks, and let me tell you now a bit about how they've been used in machine learning briefly, and then focus on ways that new families of tensor networks are being used effectively in machine learning beyond matrix product states. So, one of the kind of seminal ideas about how to apply tensor networks to machine learning was the following idea. It was put forward explored by a few groups from 2016 to 2018. And this idea was to say that a tensor network lives in an exponentially high dimensional tensor product space. So then if you want to do things like classify data with a tensor network, then the data also has to live in that space. So you take data that would be something like a vector of n entries, and you map it to a tensor product of small vectors, n of these small vectors. So now you've moved from an n-dimensional space to something like a 2 to the n dimensional space, exponentially higher dimensional space, but only in a formal way. It's really a very simple mapping where each component of x maps to a small vector, say with 2 entries. This enables you now to use a tensor network, because now this tensor product of small vectors lives in the same space as a matrix product state tensor network, or some large tensor. So you can basically imagine there's some matrix product state which could, say, classify this data and divide it up into different classes. In this case, I'm showing a model which is, gives a scalar output and is some matrix product state that represents the weights of the model, the adjustable trainable weights, applied to input data in this feature mapped form. And the scalar could tell you something like the probability of the data or the class of the data. And then there's efficient optimization or training techniques that can be used. For example, gradient descent, which can be used for all different manner of machine learning objectives, which boils down to basically removing one of the weight tensors, summing everything else in the diagram, and then using this to update the missing weight tensor, and then this can just be done sequentially. So even in this very simple proposal, there's already some very compelling ideas. You have an algorithm that scales linearly both in the training set size and in the input space size. And you have capabilities like adjusting the number of training parameters or model parameters on the fly during training with a modified version of this algorithm. So there's already some just very interesting capabilities right away by using a tensor network. And since 2016, this idea of tensor network machine learning has been successfully and interestingly ported now to other tensor network architectures. So let me tell you briefly about, very briefly about 3 of those, because they actually happen to be covered by other speakers in today's symposium, and I'll spend a little bit more time on the last one. So briefly, one of these other architectures that's not a finite matrix product state is an infinite matrix product state. This is a very nice and timely idea to explore infinite MPS, and then in particular use them for modeling language. So this group, Jacob Miller et al., used infinite MPS to model sort of these toy languages, which are very challenging to model with various grammars. And there's many benefits that Jacob will tell us about, but the idea is that you can get these models to have very few parameters and optimize them in parallel and get results that are superior to LSTM models in many cases. And most interestingly, perhaps, is that you can observe generalization from shorter sequences, training on shorter sequences, to getting correct results on longer sequences. So you're not just generalizing to missing data, but even to different sizes of outputs. So I think that's a very compelling idea. Another architecture that's now been successfully explored in a few different works is this idea called a locally purified state. So in some ways, and there's a drawing of one here and here, it sort of resembles an MPS in the sense that it's a chain-like tensor network, but it's actually been shown to be much more, to have much more expressive power while still being efficient to train like an MPS. So it's a very interesting architecture. So we've heard from Stefan Leichenauer about this work on on anomaly detection with tensor networks, where they beat some comparable state-of-the-art neural network results on tabular data. So I want to emphasize this other work too that recently came out that uses locally purified states also in a very interesting way, which is to do scalable learning of quantum channels. So these are like noisy quantum circuits that can actually be learned or backed out just from looking at observations of this quantum device. So basically one's learning what a quantum computer is doing just by looking at its output and actually getting a whole model of the quantum computer, including its noise, all in the form of a tensor network with very good results and scalability. Another example of a new architecture that's been now successfully used is 2D tensor networks. And this is really exciting to see, a very timely thing to see for applying tensor networks to image data. So 2D tensor networks ought to work a lot better in terms of expressive power than matrix product states, which have an inherent 1D structure. And sure enough, they do. You can see that for small bond dimensions, already the 2D tensor network, or PEPS, gets much better results on training and on test than MPS, which is down here. And it has many benefits, like much fewer parameters than a neural network of comparable power. And it works very well, and we can even see potentially or possibly evidence of overfitting starting to happen for larger bond dimensions due to the power of this model. And you can get really state-of-the-art results, like 91% test accuracy on the challenging fashion MNIST data set. But it has some drawbacks that I'll come back to, like the cost to train this is rather high. Last architecture that I'll talk about in this part is one that I recently explored with Justin Reyes. And this is the Mira architecture. And this is just kind of a first, attempt to use Mira in machine learning, because it has some challenges about using it that I could talk about. But the setup here is to take a fixed set of Mira layers that are fixed to encode a discrete wavelet transform. So it's like a overlapping smoothing filter that you can apply to data. We applied it to audio data. And then you do some number of these coarse grainings, and then the trainable parameters are all at the top in this matrix product state that's on top of these Mira layers. So we applied this to audio data to classify it and to try to recognize different types of sounds. These are like environmental sounds. And got good results. The key capability of why do we use a Mira, apart from just doing the coarse graining, is that we can also do fine graining, controlled fine graining backwards through the layers. And by controlled, what I mean is you can train the top layer of weights. Then after some amount of training where it saturates and you think maybe getting a finer look at the features would help, you can push the weights backwards through one of the Mira layers in a totally controlled way where the results are guaranteed to be the same after the fine graining. Then continue the training on this finer layer and do this in a way until one obtains the desired training accuracy. And we observed that this worked very well in terms of initializing the finer grain models, and we could see that having these layers helped with generalization. Actually having these Mira layers helped a lot. So we could tune the number of layers we had during training, and then you could use a validation set to see when you're still getting that generalization benefit and not go to too fine of a scale. Since I'm limited on time, I'll stop there with these examples of new architectures, but I just wanted to mention there's many others that could be talked about. So just going to briefly mention these. One is in this recent paper about medical image classification, where there's kind of a block matrix product state approach taken with this multi-scale structure. Another one where another recent application is generating image data using real quantum devices, actual quantum computers, using circuits that have the structure of a matrix product state tensor network. This is by Wall et al. So just wanted to mention those, so those of you who are interested can take a look. Let me turn now to talking about recent progress in algorithms and in theory. So this is something that is on my mind a lot, about what are better algorithms we could use to optimize tensor networks for machine learning, and what could be the benefits of that. So one recent area of understanding and of theory of tensor networks that I think poses some very interesting and pretty hard questions. What I think we can answer these questions is, why do tensor networks work at all, say in the case of two-dimensional image data, like handwriting data? Are image data sets comparable at all to low entanglement wavefunctions? Because in physics we have this understanding that that's where tensor networks succeed. That's what they're able to describe as wavefunctions or distributions that have low entanglement, which basically, after all, means low rank, so small tensor network dimension. So a tentative answer that we're actually finding from efforts by different groups, in particular this recent Google X paper by Martin et al., is no, that these image data sets are actually really highly entangled if you define the machine learning task a certain way. So if you take MNIST images and feature map them to high dimensional space using the pretty standard approaches that have been used in earlier works, then do a study of summing these images together and trying to compress them, you find that basically it's the entanglement is growing rapidly as you sum more and more images. And really you can't achieve an efficient compression of these states that are defined as sums of images. And I actually found this earlier work by Lei Wang and Song Cheng et al. And they had also done a study of the entanglement entropy of actually 10,000 MNIST images summed together with a bond dimension that I estimated to be 100 from their log likelihood results. And when I studied the entanglement of a random MPS of the same bond dimension, I see that basically they're hitting this kind of maximum value of entropy as well. So it's a similar result, showing that these are actually really highly entangled if you think of image data sets as a wave function or as something you could model with a tensor network. So does this mean that tensor networks really aren't going to work for modeling image data? But they already work, so how can this be, right? So we don't know the answer, but I'm just putting this out as like a question that deserves more of a look. One possible clue here is that it could be that supervised learning likely requires much less entanglement. And there's already some discussion about some of these ideas in this Martin et al. Paper. Another idea, though, that I think would be very interesting to pursue is that these results are clearly correct, the way this group did these calculations. But this is only up to thousands of samples. But what if one went to millions of samples? What if one did, in some sense, a sum of all possible images of, say, the digit 3, and then summed those? Would the entropy possibly start to decrease, actually, as one summed vastly more images? So there might actually be a non-monotonic effect that just hasn't been seen. And then something that group does explore that I think is worth pursuing more is that there may be that the high entanglement is somehow only in the most non-local parts of the data, which select different individual images. But then if you look at more local patches, which they do here in this lower part of their plot, that the entanglement is much more favorable. So that could be an example of where actually generalization means something like letting go of this very high entanglement structure. And that's why tensor networks succeed in practice, even though these states are actually formally very highly entangled. So the main thing I wanted to get to on this slide was to say, isn't it interesting that we can even pose and answer these questions in a quantitative way and really see what's the entanglement and really think about entanglement as a concept to do machine learning. So I think that's just an example where tensor networks should be pursued more for machine learning because we can ask and answer these questions and have some hope of progress there. Now let me switch to a different story briefly in the area of advances in theory, which is progress in training algorithms. So let me tell you a very brief story of two papers, one that I was involved in, which is about exploring different possible training algorithms for tensor networks. And the goal here is generating data from a very challenging data set. It's very simple, but it's very challenging. It's a data set of bit strings of length n bits, which have an even number of ones. So they can have whatever number of zeros, but if you count the ones, it has to be even. And so this is half of all the bit strings. So for one thing, it's a very large data set. Another reason it's challenging is that all the local correlations, say correlations between any two bits, are completely featureless and have no information in them to learn. So really all that's in this data is a kind of a global structure that you only see when you actually look at all the bits together. And so it's very challenging to learn. And now just to be a little more, give a little more details about, for the upcoming slides, the feature map used here to map from this bit string space into these tensor product spaces is just a very simple encoding of 0 bit goes to the first standard basis vector and 1 bit goes to the second. Okay, so now the first algorithm that was explored, and I have to be brief given that this is a very short talk, but the first algorithm that was explored is the idea of doing local updates to the tensor network. So this is using a matrix product state tensor network that we want to hope is going to be able to generate back this even parity data set. And what was really interesting is that using the clarity offered by tensor networks and this kind of geometric pictures that can be developed due to the linearity of them, James Stokes and John Turilla in this paper last year devised an optimal local update. So rather than doing a gradient update, they actually figured out what's the optimal update to any one tensor if you're updating them one at a time. And the update is actually turns out to be very simple. You freeze the other NPS tensors, you sum over all your training data with one removed, you take that tensor and just normalize it to be a unit vector and put it back in. And then do this on one at a time to these tensors and get a local improvement one at a time. So this already shows something very interesting, that you can use geometric reasoning to develop these kind of optimal algorithms that have very favorable scaling, linear in both data length and training set size, and get very good results on challenging data sets. So these are length 20 even parity data sets, which are very, very tough to do actually. But this algorithm does have some drawbacks. For example, it can fail if you give it a poor choice of initial parameters. So partly for that reason, but also for sort of other theoretical reasons, I was involved in another work where we were interested in the same data set, but a very different algorithm. This algorithm, I won't be able to explain in great detail, but you could call it a direct compression algorithm or density matrix algorithm. And the idea is that you define a sort of formal target tensor, which is just the equal weight sum of all the training data. Then you square this tensor with itself, but only on some of the indices. Then there's some that you leave open. And that squaring can be done efficiently. It does scale quadratically in the data set size, but it's only quadratic there, and then it's linear in everything else. And then you get a small matrix which you diagonalize, and that gives you the first tensor of your model. That gives you the first MPS tensor. Then you basically use that to sort of manipulate the data and repeat these two steps again, and you get the second MPS tensor, the third. So you basically just do some kind of straightforward sums, and you just print the MPS tensors off one at a time, and then you're done in a single pass. So because of that deterministic way that the algorithm works, it can't get stuck, and it gives deterministic results. So that gives us a hope to actually develop a more detailed theory about it. It does have the drawback of worse scaling and training set size. That's one big drawback about it. But what we did is we took advantage of the deterministic nature of this algorithm to develop a theory of generalization. So a lot of credit here to Ty Dene Bradley and John Trevilla for pushing this theory along. And what we did is we did experiments where we used different fractions of the whole data set as the training set and did an average to see how this algorithm would perform in terms of getting to the true distribution. And then we had this theory that basically just made a few assumptions to be analytically tractable, but then followed through the steps of the algorithm in a way where we're averaging over all possible training sets of a certain size. And we were able to see good agreement here, very good agreement after a certain point between the theory and the numerical experiments, which means that we have a theory here, in this case for this algorithm and for this data set and class of models, that can tell us ahead of time how big of a training set's needed to get a certain quality result. And I think that's a very nice result that could be generalized a lot more, and I'll come back to that point. But just to say that tensor networks give us that capability to develop theories like that. So we need a lot more theories of that type. There's many other areas of theoretical development going on. I'll just say one more slide about that, just to point your attention to these other developments. One is this recent work by Glasser et al. Where they do a very comprehensive study of expressive power of different tensor network architectures, like many different ones with positive weights or complex weights or different structures. Another paper is Hasha Mizada et al., which is this paper, Adaptive Tensor Learning, where that group studies an algorithm where they can actually figure out the topology of a tensor network from the data, not just the parameters inside. And another paper I was very excited about is called Tensorized Random Projections, which shows the proper way to use random tensor trains in kind of a randomized SVD algorithm in a much higher dimensional spaces. So let me now kind of wrap up. So why did I tell you about these different architectures and different algorithms? One reason is to point to where we have more work to do, those of us who are interested in pushing this field forward of tensor network machine learning. But where there's also a lot of hope. So I think we have hope from these powerful results that I showed you and these new architectures that are very capable. And we have hope from theory, where we see that we've only just kind of scratched the surface of the theory we can do, and this could feed back in to better results. So what are the big obstacles right now, as I see it, in this field in terms of results? Well, one is that the cost to train these architectures, these tensor networks, in terms of memory and time, despite having good scaling, can actually still be rather high in practice. Another downside is that it's still a very new topic, so the best architecture choices, for example, whether something like convolutional layers should be used to preprocess the data, or which tensor network is actually best for one-dimensional data, these are being explored still, and it's not so obvious about these, and so that needs more time. But I think there's reasons for optimism, very, very strong reasons. One is that there's still a lot of tricks and techniques that are barely have been used yet. So one is using sparse tensors within the tensor networks. And a very common family of this in physics is block sparse tensors. And these actually map onto interesting concepts in data. For example, symmetries of the data, or some kind of conserved quantity. Like you could think about the amount of ink on a paper as something that you would conserve and limit. And this could be mapped into a block sparse structure of the tensors. Infinite tensor networks could be used more, so infinite PEPs, infinite 2D tensor networks for images. And relatedly, symmetries could be used more. So convolutional layers have already been seen to help. Translation symmetry could also be exploited more to get parameter reduction and efficiency and better generalization. And finally, a really ambitious one would be to use the theoretical insight in tensor networks to devise more data-efficient approaches. Another opportunity is just itself to advance the theory of machine learning using capabilities of tensor networks. So one thing that could be done, I believe, is to really characterize quite fully what data is learnable by a given type and size of tensor network. So that could include simple statements like about scaling and range of correlations, but there might be much more fine-grained statements about properties of data like locality of features that connect to supervised labeling objectives that could be studied. This theory of generalization that I highlighted also in this work by Bradley et al. Could be improved quite a lot. So there's a lot of room for improvement, which I think is very exciting. So there could be tighter bounds, including rigorous probabilistic bounds on generalization performance. This theory could be extended and applied to other toy data sets and maybe real data sets. And then if the theory develops far enough, I could envision that you could encounter a new data set, compute summary statistics of that data set, then just from that already know what kind of results you might expect from a certain tensor network in terms of generalization power and performance. There's other training algorithms too out in the literature that I don't think have been applied enough to some of these data types like image data. So for example, the TT-cross algorithm or the idea of using the CUR decomposition inside tensor networks, which has been explored some in engineering literature. And all this progress in theory will feed back into better results. So if we pursue this theory, then that'll also mean better results. So these things are very coupled together. So one last thought, and then I'll be done, is that tensor networks really likely are not just kind of a niche physics tool or something that is of interest to a few practitioners, but really I think we'll look back one day and view it as the right way to do linear algebra in very high dimensional spaces. So if you think that machine learning has something to do with high dimensional spaces and linear algebra, then in some sense you're sort of forced to think about tensor networks for the benefit of hindsight. And I think an exciting a belief that I have is that we haven't even figured out all or even most of the biggest pieces of tensor network technology. Like for example, if we have a matrix-like tensor network, like an MPO, what's the analog of the QR decomposition or the SVD for that? We don't even really have that in like a deterministic form, but I think we could. So I think there's a lot of like latent power in these ideas. And some of the most major progress only just happened in the last year, like for example, canonical forms of PEPs or progress in randomized algorithms. So I think there's a lot of room for reason to be excited and a lot of room for progress, especially on the theory front. So thanks for your attention.